thanks everyone for coming along this afternoon. It's a beautiful sunny day here in Sydney. Hopefully it is across the rest of the nodes. I'm excited and delighted to introduce Ludwik Kranz. As those that were on here originally will know, that he submitted his thesis within a week ago. So it's just a couple of days ago. It's been fantastic. I'm not going to give away what his thesis is about because he's got a question up on the slide there. But Ludwik came to us, I guess, in 2016, did an Erasmus Master of Nanoscience in Leuven in Belgium. Originally comes from Poland and has had a fantastic PhD with some exciting results. So with that little introduction, I'll introduce him and take it away, Ludwik.
Thank you for your introduction, Michelle. So I wanted to kick it off with a little brain tickler. I'm sure some of you know where I'm going with this, but what do the following have in common? Heartbeats, music, ocean currents, and stock market. Well, it turns out that if you analyze the signal in the frequency domain and plot the power spectral density, it will be inversely proportional to the frequency for all of these different phenomena. And let me explain what I mean by this exactly. So there's different types of noise, which I show on the left here, and on the right are the corresponding power spectral densities plotted in a frequency domain on a logarithmic scale. So for example, the white noise, for white noise, you have you have like this flat distribution of power, which means that power is equally distributed over all the frequencies. Pink noise is basically synonym of 1 over f noise, and brown noise is 1 over f squared. And so for like pink noise or brown noise, you can see that the power is mostly distributed over the lower frequency, over the lower frequencies, and this manifests itself in this like slow drift in the signal. And on the right-hand side, I enlisted some phenomena that can be described by different noise types. And the things that I had on my first slide, they actually all exhibit approximately 1 over f spectral dependence, which is very interesting that 1 over f noise is found so commonly in nature. And as far as I know, it's still like an unanswered question as to why it's so commonly found, but I'm not going to try to answer this question. Instead, I'm going to focus on the fact that 1 over f noise is also found in electronic devices. So for instance, if you were to measure electronic device of a resistor or a transistor, you're likely to find 1 over f dependence. And that has been also shown for different materials. So for example, for metals, for semiconductors, or even vacuum tubes back in the day. So in my talk, I'm going to talk about 1 over f noise in semiconductors, which is often referred to as charge noise. And I will particularly focus on silicon. And the results I'm about to present to you were published last week in Advanced Materials in this paper entitled Exploiting a Single Crystal Environment to Minimize the Charge Noise on Qubits in Silicon. So I encourage you to go check out that paper. Okay, so the charge fluctuations, or like the electronic fluctuations in semiconductors, are believed to originate from defects or charge traps that can trap and release the electron. And if you have a lot of these traps that at random are capturing and emitting electrons, they collectively give rise to electronic fluctuations. So where do these defects come from? Well, let's look, for example, at the interface between silicon and silicon oxide. So what we have here is basically a phase transition between crystalline phase and amorphous phase. And in principle, the defects can be found anywhere in this picture. However, in electronic devices, the wafers are already grown as a single crystal, so with really low defect density. So you would expect relatively low defect density in a crystal itself, and the literature points out that the defects are more likely to be found on those interfaces between different materials or in the oxides themselves. So every such trap that's capable of trapping and detrapping the electron can be understood as a two-level fluctuator that switches at random between two different states, which can be represented with this simplistic energy diagram here. You can think of it, for example, as an electron tunneling between the two sides with frequency, switching frequency Fs. And in order to switch between the two sides, it needs to overcome the energy difference, which we'll call activation energy. And these two-level fluctuators are believed to be thermally activated, which means they follow this rate equation. So what this means is that as you increase the temperature, the switching basically gets faster, and in the low temperature limit, you will freeze out in one of these states. So this is like an example of a signal produced by a two-level fluctuator. You basically switch between two states, and this is also known as a random telegraph signal. And this is the corresponding power spectrum density of a two-level fluctuator. So it's described by the Lorentzian function. And if you look at the spectrum, it's characterized by a flat spectrum up to the switching frequency, and then it drops off as 1/f squared. And interestingly, you can construct 1/f noise using only these Lorentzian functions, which is schematically shown here, where in light blue I showed the individual Lorentzians, individual contributions, and if you add them all up, you can get 1/f noise. So this collective 1/f noise would correspond to a collection or an ensemble of two-level fluctuators that collectively give rise to this 1/f noise. And this is, usually what people talk about 1/f noise semiconductors, they associate it with an ensemble of two-level fluctuators. And this 1/f frequency is found, at least in this frequency regime between the slowest and fastest switching two-level fluctuator. And this equation that I provide here is the equation that describes the spectrum in this intermediate frequency regime here. And I want to point out to this term D at the end, which represents the distribution of activation energies within this D term here, distribution of activation energies within this ensemble of two-level fluctuators. So I just want to make one more comment about that. So 1/f noise can be actually obtained only if this distribution of activation energies is flat. So for example, if your all activation energies within your ensemble are the same. But in more general case, if, for example, your activation energies of your two-level fluctuators are different from each other, then in more general case, you would have a power law frequency dependence described by this function 1/f to the power of alpha, where alpha can be different from 1, but typically is between 0.5 and 2. I'll switch gears and tell you why we're interested in this. So in the group led by Professor Michael Simons, we try to develop hardware for quantum computers, and we work with electron spin qubits. So what I'm showing here is a energy diagram of a energy well or a confining potential, where we can put an electron and apply to split energy levels of a spin down and spin up. And we can use these energy levels to encode our qubit, the basic building block of a quantum computer. And in practice, we achieve this confinement potential using phosphorus atoms in silicon, so which is shown on the right here in the schematic, where the red dot here represents a phosphorus atom within the silicon crystal lattice, where the phosphorus atom replaced one of the silicon atoms. And the orange sphere corresponds to the electron wave function. And it's important to know that the phosphorus atom is a donor, so it donates this electron to the system. And we perform experiments at cryogenic temperatures, where this electron doesn't have enough thermal energy to go into the conduction band, and instead it will freeze at this site of the donor. And our ultimate goal with this technology is to, create multi-qubit architectures where electron speed qubits could coexist with charge sensors and control circuitry, so that we can, control the qubits and reload the qubits and execute quantum algorithms. So let me briefly explain how we fabricate our devices. So we start with a bare silicon chip with a monolayer of hydrogen on top, and then we approach with the tip of scanning tunneling microscope, and by applying voltage, we can write any desired pattern into this lithographic mask. We then expose the sample to phosphine gas. Phosphine is pH-free, and the phosphorus P is represented with red here. And these molecules will react with the exposed surface of silicon. We then heat up the sample to incorporate phosphorus atoms into the silicon crystal lattice. And finally, we grow a protective epitaxial layer of silicon on top of that. And all of these steps are done in ultra-high vacuum. And after that, we remove the sample from the vacuum, and we use standard clean room post-processing methods to contact this buried donor device. So this here is the STM image of the device that we use for the noise measurements that I'm going to present. So this image was taken after the STM lithography. So the light regions here correspond to the regions where we disturb the hydrogen mask, and the darker regions correspond to regions where we still have our hydrogen mask. In the center of this image, we can see two qubits. This is the prototype 2-qubit device. Below that, we have this Y-shaped island, which is single electron transistor, SET, tunnel coupled to the source and the drain. And we also have 4 electrostatic gates around that to control the electrochemical landscape of our qubits. And in this particular device that we're measuring, we have encapsulation layer of 40 nanometers. And when we remove the sample from the ultra-high vacuum, we would have native oxide naturally forming on the surface. Okay, so in this seminar, I'm going to present you 3 different methods of measuring charge noise in such a device. And for the first method is SET spectroscopy. So the spectroscopy using a single electron transistor charge sensor. So for this method, we use basically this bottom part of our device. So we basically use the charge sensor to kind of detect the fluctuations in electrochemical potential in this device. So first, let me explain briefly the working principle of a charge sensor. So if we look at if we take the energy diagram along this red line here, we have a source with, a filled up to Fermi energy. Then we have a tunnel gap. Then we have the SET, which can be understood as a quantum dot with quantized energy levels. Next, we have another tunnel gap, and then the drain. Now, when we apply a bias voltage between source and the drain, we can force electron, to tunnel between source and the drain via the SET. And what I'm showing here at the bottom plot is current through the SET as a function of the voltage VSET. And this refers to the voltage applied to this bottom gate here. And by applying voltage to this SET gate, we can basically shift the energy levels of the SET up and down. And the regions where we see high SET current correspond to the situation where we have energy level in between source and the drain energy levels here that can facilitate the tunneling from source to drain. And regions without current correspond to situations where we have no available energy states and SET is in Coulomb blockade. Okay, so now I zoom into one of these Coulomb peaks. So what I'm showing here is again one of these Coulomb peaks. And what I want to do now is I want to tune this charge sensor to its highest sensitivity so that I'm going to be sensitive to any fluctuations that are intrinsic to the device. So how do we find the highest sensitivity point? Well, we calculate the derivative dIdV, which is shown here at the bottom, and we find that maximum sensitivity point is found here at the side of the peak, which means that if you change the voltage, slightly, you get big difference in tunneling current. So by setting the voltage to the side of the peak, we acquire a time trace. Basically, we record the tunneling current as a function of time, and then we calculate the corresponding power spectral density of these current fluctuations. So this is shown here on the right. The dark trace corresponds to the data taken on the side of the peak, and we can obtain this power spectrum. And for comparison, we take a similar data set, but taken on a top of the SCT peak. So on the top of the peak here, we have high tunneling current, but the fluctuations in current are smaller because this tunneling current is less sensitive to any changes in electrochemical potential. And this can be seen, this reveals itself because this light blue trace taken at the top of the SCT peak is actually lower. So it means that the fluctuations in current are actually smaller on top of the peak. Okay, so by doing this comparison of data taken on the side and on the top of the SCT peak, we confirm that the fluctuations in tunneling current are dominated by fluctuations in electrochemical potential in this device. So having confirmed that, we go back to the measurements on the side of the SCT peak. And so first we want to figure out what kind of equation, what kind of function would describe the spectrum that we measure. So we find a good fit with this equation shown here, and the fit is shown with this dashed line. And this equation basically has two contributions, the power law contribution and the Lorentzian contribution. So as I mentioned before, the power law spectrum, the power law function would correspond to an ensemble of two-level fluctuators, while a Lorentzian function would correspond to a single two-level fluctuator. So we think we have combination of both in this device, and this has been observed in other systems as well. So the fact that we observe a Lorentzian contribution to our spectrum is perhaps not surprising, because this is something that was observed before in this paper that I'm showing here. So what they observed is also this like Lorentzian contribution at around 1 Hertz. And what authors of this paper did is they calculated that the switching frequency of around 1 Hertz corresponds to the statistical distribution of charge traps at the silicon-silicon oxide interface. So we think that, and for our case, the Lorentzian shoulder is around 7 Hertz. So, it's the same order of magnitude, and we believe that this Lorentzian can potentially come from the defects at the surface. So in general, we have the power law contribution to our spectrum and the Lorentzian contribution, with this power law being in the lower frequencies. And from now on, I'm going to focus in this low frequency regime, because it's the low frequencies, that dominate the overall charge noise if you have 1/F dependence. But I also want to mention that I know that other groups went to higher frequencies, and this is definitely something we're interested in exploring the high frequency regime in future as well. So if we go to lower frequencies, so this is similar measurement, just a bit longer. So we go to lower frequencies, and we see that this power law frequency dependence prevails to lower frequencies. And actually what I'm showing here now is the fluctuations in the electrochemical potential. So the units of these fluctuations are now in absolute energy scales, and the translation between the fluctuations in current that I showed on the previous slide and the fluctuations in electrochemical potential that I'm showing on this slide, the translation between the two is given by this equation. So maybe I can explain this quickly. So first of all, you need to consider how much the change in current is caused by a changing, for example, a voltage using your control gate. So you have to consider this factor, the IDV. And on the other hand, you also need to take into account the lever arm, which kind of converts the voltage fluctuations into absolute energy scale. So basically what we derived here is the spectrum of fluctuations that describe the fluctuations of these energy levels of the SCT. So it's like the shaking of electrochemical potential in this device. And the fact that it's expressed in absolute energy scales will help us later to compare between different methods and even between devices. So this concludes the first measurement method, the SET spectroscopy. Now I'm going to move on to the second method, SET peak tracking, which we use to extract noise at even lower frequencies. So what we do here is we scan over the SET peak over and over again. And what I'm showing on the right is the SET current as a function of measurement time. And this bright line here corresponds to where our SET peak is. And for every trace, we perform a fit function, and this allows us to basically map out the position of the peak as a function of time. So we would attribute these changes, these fluctuations, again, to some interesting noise in a device that shakes the electrochemical potential of the SET. So this is the data from this measurement. So this is our trace in time domain, and we can translate it into the power spectral density in a frequency domain. And to get a better insight or like better understanding of this data, we use Welch method, which is a well-known method for processing power spectral densities. And what we do here is basically we divide our data in time domain into windows. And for each window, we calculate power spectrum density independently, and then we average over all the windows. So what I'm showing on this plot here is with blue data is the raw spectrum, with green data is the Welch method with only 2 overlapping windows, and the red data points correspond to Welch data with 10 overlapping windows. So you can see using this Welch method, we can get less variance and better estimate of our noise, but we sacrifice some of the lower frequency information because we're effectively squeezing the data in the time domain. But nevertheless, from this method, we can see that the power law frequency dependence continues into these lower frequencies, which brings me to the third method of measurements, which we will use to map out even lower frequency regime. So far, I showed you 2 methods, SET current spectroscopy and SET peak tracking. And for both methods, we used charge sensor itself as a probe for charge fluctuations. In the third method now, I will use qubits as a kind of a probe to measure charge fluctuations in the same device. So if we zoom into this region here, we can see the top part of the SET and the 2 lithographic openings that host our qubits. And by performing electronic measurements at cryogenic temperatures, we can characterize the device in terms of charging energies and relaxation times. And based on this information, we can determine the number of donors in each lithographic opening. And in this case, we have 3 donors in a left dot and 2 donors in a right dot. And they are separated by 12 nanometers. And we operate this device in 1-1 charge configuration, which means we basically load 1 electron on each qubit. And the donor qubits, they provide very strong, very sharp confinement potential, schematically shown here, so that if we load 1 electron on each qubit, the wave functions are actually pretty small, like 2 or 3 nanometer Bohr radius, so they can be understood as independent wave functions. However, if we use gate voltages on the opposing gates, we can create this kind of a tilt in electrochemical potential. And this tilt we call detuning, because we're detuning the energy levels of 2 dots with respect to each other. And by controlling this detuning, we can go to 0 charge configuration, where we basically force both electrons to go into the same quantum dot. And we can control this. We can go somewhere in between, where we can control the overlap between electron wave functions, which gives us some finite value of exchange interaction. So this is the charge stability diagram of our device. So the diagonal lines correspond to the SET lines or Coulomb peaks. So every line is like adding 1 electron to the SET. And we can also see these breaks in the SET lines that arise as we add electrons to our qubits, because that effectively shifts the potential of the SET as well. So by analyzing this charge stability diagram, we can figure out how many electrons we have on the qubits in every region. So for example, if we apply negative voltages, we can deplete our double dot system. And if we apply positive voltages to the gates, we can load as many as 7 electrons to this double dot system. But for measurements, I'm going to show now, we tune the device to this 1-1 charge configuration. This is zooming into this gate map and shows you 1-1 and to 0 charge configuration. And basically by setting voltages to this along this red line, we can control this detuning in electrochemical potential and control the, the overlap between the electron wave functions. So what we do in the experiment, we start with in 1-1 region with separated electron wave functions. We then perform this detuning pulse to overlap two wave functions, and we time that, and then we separate the wave functions again, and we perform independent spin readout on both qubits. So with this pulse sequence, we get this data. So what I'm plotting here is the probability of measuring up-down state as a function of duration spent at this point 2 over here. And we see that this probability oscillates, and these are called exchange oscillations or coherent swap oscillations. And the frequency of these oscillations directly corresponds to the exchange interaction J. And we see a decay in oscillations, and by feeding Gaussian function, we can calculate the dephasing time T2 star. Okay, so now we repeat this experiment at different detuning positions, and this allows us to plot oscillation frequency as a function of detuning. And as expected, if we increase this detuning, the overlap between two electron wave functions is larger, and this leads to faster oscillations. And we feed this data with this equation here, which is derived from Hubbard model. And you see the exchange interaction is not only dependent on detuning, but also on this parameter here, TC, which stands for tunnel coupling. And for now, we use the tunnel coupling as a feed function, and by feeding the data, we get a tunnel coupling of around 2 gigahertz for this device. And in our devices, the tunnel coupling parameter is linked to this inter-qubit distance, which in this case is 12 nanometers. And we actually noticed that tunnel coupling is very sensitive to this distance. And so this device has been engineered on atomic scale to kind of get this appreciable tunability of exchange interaction with gate voltages. Okay, so now I'm going to try and give you more intuitive understanding as to why we have decay in our exchange oscillations. So if you set voltages to a certain detuning position, you will actually have a distribution of values, of your detuning values, because of the intrinsic noise in the device that shakes the electrochemical potential. So for now, let's assume it's a Gaussian distribution of values, and therefore you will not get a single value of J, but you will actually also get a distribution of J values. And this mapping between distribution of detuning and J values can be described by this equation here. You basically have to take into account the derivative dj d epsilon. So what this means basically is that for a given detuning noise, if you go to lower detunings, you will get smaller J noise because at this point you have your dj d epsilon is smaller. This function is less steep. Okay, so since you have distribution of J values, this means that every time you go to every time you do your exchange pulse, you will actually sample values from this distribution, and every experimental trial, you will get slightly different oscillation frequency. And if you average all of these trials, you will get dephasing of in your oscillations. So this is the standard T2 star procedure. So we would expect T2 star to be inversely proportional to J noise. And everything that all the different things that I just said can be summarized in this master equation that links detuning noise to T2 star and dj d epsilon. And this equation and this methodology in general is a standard method to calculate detuning noise in double dot devices. And this is great. Now we can use this method to calculate sigma epsilon in our device. So for the data I showed you previously, the T2 star time was around 200 nanoseconds, and I know the detuning at which this data was taken, and therefore I can calculate dj d epsilon at this position, and I can plug all of these values into my master equation, and I'm getting something like 4.4 micro EV of detuning oscillations. And this is in absolute energy scale, micro EV. So you might think it's a good measure of charge noise in your device. And actually, yeah, this is something that people report for different devices. But actually, as I'm going to show you now, it's not really that good metric. So basically, what we did, we assumed this kind of Gaussian distribution of detuning noise, which implies that the noise would be white. But as we know from like the first part of my talk, the noise that governs the charge fluctuation has 1/f dependence. So to investigate this in more detail, we measure T2 star as a function of total measurement time, and we see a measurable, decrease in T2 star over time. And for every data point, we can calculate the corresponding sigma epsilon, and we see that it's changing with the total measurement time. So for example, by reducing the total measurement time to 1 hour, we get a sigma epsilon of something like 2.5 micro EV. Okay, so to understand and quantify this kind of change of noise with total measurement time, we go back to theory, and the theory tells us, well, regardless of what spectrum of noise you have in your device, your fluctuations in detuning are described by this equation, which is basically integral over all frequency components. So if I was to visualize it, if the red line is the power spectrum in a device, then sigma epsilon would correspond to the square root of this area here. However, for the experiments, we can limit our considerations to certain frequency range. In particular, the lower frequency, the lowest frequency that can couple to your experiment can be written as 1/, total measurement time. Okay, so we can put a finite bounds on this integral now. And using this equation and assuming that the noise has power law spectrum, we actually get a really good fit to our data. So this tells us, okay, the noise that's causing fluctuations in the detuning between our two qubits is governed, it comes from an ensemble of two fluctuators that's causing power law frequency noise. But we actually went one step further, and knowing the exact increase of noise with time, we can actually calculate the exact spectrum of noise in this frequency regime over which we're changing this lower boundary of the integral. So these are the results here. So, by changing the total measurement time, we're able to plot, to measure detuning noise spectrum in this very low frequency regime. And this is great because now we can compare this data with the previous two methods that I described earlier. So this is the combined noise spectrum in this device. This is like a summary of all the measurements, where blue data shows you the SCT current spectroscopy, red data shows you the SCT peak tracing, and the yellow data shows you the T2 star measurements. And this is like the final outcome of our noise measurements. But based on this, we can draw several interesting conclusions. So first of all, we noticed that these methods kind of complement each other because they basically can be applied at different frequency regimes. So by using a combination of these methods, we're able to obtain noise, collectively over 4 frequency decades. And using this collective noise spectrum, we can fit the data, and we obtain power law frequency spectrum described by this equation. And basically, you need 2 parameters to describe power law frequency spectrum: S0 and alpha. S0 gives you like the overall the vertical offset of this line here, and alpha gives you the slope. And because we've taken data over 4 frequency decades, we were able to determine these parameters with high accuracy. So I just want to comment on these values that we measure. So for alpha, we measure 1.63, which is not really pink, but not brown as well. It's something in between. We need a new color for this to describe noise in this device. But what it tells us is that the noise is dominated by ensemble of two-level fluctuators with non-uniform distribution of activation energies. And we also can conclude that some of these two-level fluctuators have really low switching frequency because, you know, we haven't even reached the limit of this parallel spectrum. Okay, going to the second parameter that we extracted, S0. This is actually expressed, so we measure 0.0088 microelectronvolts squared per hertz. And, you know, these are, again, the absolute energy scales. So we can actually compare this value to what has been previously reported. So this comparison is done in this table where we compare to previous results in quantum dots. And the noise measured is given here. And it's actually significantly smaller to what has been previously reported. And we conclude that, you know, this is because of the our device is basically embedded in a single crystal of silicon with no other foreign material in there and away from any interfaces and oxides. So definitely the fact that we have such a low noise level in this device, we attribute to, you know, the fact that this device is separated from the oxide with this encapsulation layer. The other interesting thing that we notice is that, you know, we used SET measurements for first methods, and then we used Qubits for the third method. And yet we see, you know, that the spectrum follows the same frequency dependence. So this suggests that the noise dominating the noise on SET is, you know, similar to the noise on the qubits, perhaps coming from the same ensemble of two-level fluctuators. And, you know, based on that, we thought, okay, maybe when testing devices, it's sufficient to take just a simple spectroscopy data, which is fairly straightforward measurement. And based on that, we might be able to estimate, you know, the noise that qubits are going to be experiencing. So how would that work in practice? Well, we can measure noise spectrum, and then if we can estimate the total measurement time, we can basically calculate this integrated noise sigma epsilon. And based on that, we can even go a step further and think, okay, what kind of fidelities of the qubit gates we can expect, you know, given this level of integrated charge noise. So what I'm showing here is the result of such modeling for a squared swap gate. So this is squared swap gate fidelity as a function of total measurement time and the noise in your device. And this modeling is done just by time evolution of the Hamiltonian of our, you know, two-electron spin system, and we take into account detuning noise, and we compare it to the case with no noise whatsoever, so like ideal squared swap gate. And then by comparing these two, we can, you know, get estimate of the two-qubit gate fidelity. So this gives us like an upper bound of achievable two-qubit gate fidelities given this integrated noise. So what we can see from our modeling is that to reach this desired high fidelity two-qubit gate region, we have to first of all reduce, you know, have really low noise in our device, which we hope we can achieve with our crystalline environment hosting the qubits. And on the other hand, we need to be able to perform you know, our experiments as fast as possible, so to reduce the total measurement time and to avoid these, you know, low frequencies of noise. So we think we can improve upon this by optimizing the readout time. So for experiments I showed you earlier, actually the readout time and initialization time of the qubits, you know, it takes the most of our experimental duty cycle. So we think we can improve upon that in future by engineering faster tunnel times between the qubit and the reservoir. So this brings me to the conclusions. So we showed 3 different methods of measuring charge noise: SET spectroscopy, SET peak tracking, and dephasing measurements on the qubits. And we applied them to different frequency ranges. Based on these measurements, we extracted the overall noise spectrum in our device, which follows the parallel frequency dependence over at least 4 frequency decades. Moreover, from T2 star measurements, we were able to calculate the standard deviation of detuning fluctuations sigma epsilon, and we showed that this depends on the total measurement time. And we also showed that these two metrics are correlated. So up to now, when for electron spin qubits, people would either report the noise that's coupling to the charge sensor or the noise that's coupling to the double dot detuning. But we showed that, well, at least in our device, we found that this relationship is well described by this beautifully simple integral. And the fact that we have overall low noise in our device, we attribute to the crystalline environment hosting the qubits and the fact that we're separated from this interface with oxide. So going forwards, we definitely want to further improve the charge noise characteristics in our devices. So we think there's at least two ways in which we can do it. First of all, we can improve the single crystal in our device. So basically, this encapsulation layer above our device is something we grow ourselves in a growth chamber, and we think that we can further optimize this growth to have even less two-level fluctuators in this layer. And secondly, we recognize that going forward, it's going to be important to execute quantum algorithms really quickly. So we think we can achieve this by speeding up our readout. And from our previous results, we know we can execute single-shot readout at around microsecond scale. That was achieved in different devices. But we estimate that by combining low charge noise characteristics with this really fast readout, we can possibly achieve really small integrated noise of below 1 micro eV. And we can also estimate that with realistic values for noise, the 2-qubit gate fidelities as high as 99.99% are in reach using donor devices. That's all. Thank you.